Hey there, guys. It's Abhiram here, and today is the birthday of Albert Einstein. I hope you know this guy. Einstein is popular for developing the special theory of relativity, which is known for its perception of time. You might have heard about time being faster for some people and slower for some people in the perspective of the special theory of relativity. If you happen to be a person who has heard a lot about the special theory, but you want to know it in greater detail, this is a good point for you to start. Today we will be discussing why do we have the special theory of relativity? Where did it come from? To solve what problem was it developed? So on and so forth. We will start by trying to understand certain basics, and then we will give ourselves a historic context in which the theory was developed, and then we will delve into the theory itself. Right? So before anything else, we need to know the meaning of two words, the difference between two words, absolute and relative, the way we use it in physics. We will try to make ourselves understand what these terms mean by going through a bunch of examples. Okay, so here I have a basket of apples. It is a basket with a bunch of apples, and I can ask a question: how many apples there are inside the basket? Okay, and I ask this question to you. Here you are. This is you. So you have to count how many apples there are and tell me how many there are. You know how to count, so you look at them, you count them: one apple, two apple, three apple, and you tell me, Abhiram, there are three apples. Right? But I'm not convinced. I'm not satisfied. I want to cross check with someone else. So I ask your friend the same question, but your friend happens to be moving in a bicycle. He's going to the left on a bicycle. As he moves to the left on his bicycle, he looks at the apple, he counts them one, two, three, and he tells me there are three apples. I am still not satisfied. I want to go for a third person. So I ask one more friend of yours who is climbing down a ladder. He looks at the apples while he's climbing down the ladder, while he's getting down. He counts, he knows how to count one, two, three. He tells me there are three apples. Alright? So what we did here is we asked the same question, how many apples there are in the basket, to three different people doing three different things. One guy is standing still, another person moving in a bicycle, another person getting down a ladder, and they all gave me the same answer. Three, alright? So keep this in mind as we move forward. Now let's look at a different example. Let's say there are a bunch of trees, an apple tree, a mango tree, or a cherry tree, or whatever. And this is you again. Now I can ask you a different question. Which way are the trees moving? Which way are the trees moving? When you listen to this question, you will tell me, what sort of question is that? The trees are not moving. They are standing still. They are there. They're not moving at all. Trees don't move on there. They're not moving at all. That's what you'll say, right? But I am not convinced. I want to ask the question to someone else. So I ask this question to your friend, who is this time moving in a car to the left on my screen with a speed of 70 kilometers per hour. That's too fast. Now I ask him, which way are the trees moving? Now he looks outside his window as he is driving the car, and as it appears to him, the trees look like they are moving backwards. We all know this, we have all experienced this in our lives. When we were kids in our childhood, we were amazed at the sight of trees and buildings moving backward as we moved forward in some vehicle. The same way, when your friend looks outside his window, he sees that the trees are moving backward. Backward for him is right side on our screen here. So he says they are moving to the right. I want to check this with one more person. So I ask this to one more friend of yours who's moving in a bicycle to my right on the screen with a speed of 30 kilometers per hour. She looks at the trees. She also, as it appears to her, says that the trees are moving backwards, which is to the left on my screen. So she says they are moving to the left. Alright, so we see something different is happening here. Alright, I have asked the same question to three people and they are giving me three different answers. So this was a qualitative question. Now let me ask a quantitative question. How fast are the trees moving? With what speed are they moving? Okay, so let's not worry about how these people can actually measure the velocity, but let's say they've got a good intuition for guessing the velocity or whatever. So I'm asking, how fast are the trees moving? Now you will obviously tell me the trees are not moving, so their speed is zero. Right? You'll tell me the trees are there. They're not moving. Their speed is zero. But your friend here on the car, when he looks out, he is moving to my left with a speed of 70 kilometers per hour. So when he looks outside his window, he sees the trees are moving backwards really fast, roughly 70 kilometers per hour. So he'll tell me that they are moving to the right 70 kilometers per hour. By the same token, your friend here going to the right with 30 kilometers per hour will tell me that she sees the trees moving to the left with 30 kilometers per hour. All right. So I hope you can make sense out of this. Previously, when we had a bunch of apples in the basket and asked people to count the number of apples and tell me how many apples there are, different people in different circumstances gave me the same number. Whereas this time, I'm seeing something different. Different people in different circumstances are reporting different numbers. Let's take one more example to make ourselves more familiar with this. Instead of the trees, let's say there is a horse running to the left with 70 kilometers per hour. I want to leave this as an exercise to you. Suppose if I ask the question, how fast is the horse moving? What would your answer be? What would the answer be of your friends? What number would they tell me? Okay, try to get an answer to this by yourself and take it as an exercise. All right. We started by trying to understand the meaning of two words, absolute and relative, and we looked at a couple of examples. First, we had an example where different people in different circumstances, some people standing still, climbing down a ladder, or moving in a bicycle, so on and so forth, had to count the number of apples in the basket and tell me how many apples there are. And all sorts of people in different circumstances reported the same number, right? So, and in fact, you can ask this question to many different types of people doing many different sorts of things. And if they know how to count, they will all report the same number. As in this example, everybody said there are 3 apples in the basket. So we say that the number of apples in the basket is an absolute count, because all sorts of people in different circumstances, if they know how to count, they'll report the same number. They will agree with each other. That's why we say that number of apples is an absolute count. In the same way, if any other quantity behaves in the same way as the number of apples in the basket, we say that that quantity is absolute. Right? On the other hand, we have motion, the motion of trees and horses. In our previous example, we saw that different people perceived motion differently. The motion of the trees appeared differently to different people. For one person, the trees were just standing there. For another person, the trees were moving backward. For another person, the trees were moving in a different direction. Right? So motion appears differently to different people. We tend to call these people as observers in special theory, but I'll get back to that. Different observers will report different values for the velocity, as opposed to the first case where different observers reported the same number for the count of the apples. Here, different observers are reporting different numbers. So we say motion is relative, which means whatever number an observer tells me, that number is true relative to that observer. That's what I mean when I use the word relative. Okay, so the number of apples in the basket is absolute. As on the other hand, motion is relative. So I hope you understand the difference between absolute and relative by this point. I want to convince you that motion is relative. Measurements of velocity are relative. And the best example I can take, the best way I can do that is the earth and the sun. Right? If you stand on the surface of the earth and look at sun, you see the sun rises, the sun sets, the sun moves around the earth, right? The sun moves in the horizon, the earth is not moving. There is sunrise, there is sunset, and all sorts of things. But if you get out of the surface of the earth, if you stand in outer space and look at the same system, you will say, oh no, it's not the sun who is moving. It's the earth that is moving around its own axis, right? So you see, if you depending on your circumstance, if you are standing on the surface of the earth, you would say it's the sun who is moving. The motion is attributed to sun. If you were outside, you would say the sun is standing still. It's the earth that is rotating around itself. It's the motion is attributed to earth. So with this example, it's pretty clear that motion is always relative. The sun is moving, but relative to a person standing on the surface of the earth. Whereas the earth is moving around its axis relative to a person outside earth, a person looking at the earth from the outside. Okay, so I hope from this example you are convinced that velocity measurements are relative. To give ourselves a feel, let's look at a bunch of numbers. If I ask you what is the speed of Mount Everest or what is the velocity of Mount Everest, if you happen to stand on the surface of the earth, you would tell me that Mount Everest, it's a huge mountain, it doesn't move at all. It has no speed, it has a zero speed. On the other hand, if you happen to be situated at the center of the earth, let's not care about how you might get there or how you will survive at the temperature, but if somehow you got to the surface of, center of the earth, you would say that Mount Everest is moving around you with a speed of 1600 kilometers per hour. Why? Because we all know that the earth rotates around its own center, and Mount Everest is located on top of Earth's surface. So Mount Everest will also move around the Earth's center. So an observer standing at the center of the Earth will say Mount Everest is moving around me at a speed of 1600 kilometers per hour, as opposed to a person on the surface of the Earth who says the Mount Everest is not moving at all. Now I'm going to send you to Moon. I'll send you to Moon. You're standing on the surface of the Moon, and now you will say Mount Everest is moving not with a speed of 1600 kilometers per hour, but with a speed of 3600 kilometers per hour. Because if you're standing on the surface of the moon, just like people on Earth see the sun rising and the sun setting, people on moon will see the Earth rising and the Earth setting. And that happens with this particular speed here. Right? So since Mount Everest is located on top of Earth's surface, you will say Mount Everest is moving around with this speed, 3600 kilometers per hour. Now I'll send you to the surface of the sun. Right? Now don't ask me how you will survive there, how you will make sure you won't be roasted to death. But if you stand on the surface of the sun, obviously in both these examples I'm ignoring the velocity due to rotation of the earth. If you stand on the surface of the sun, you will say that Mount Everest is moving with a speed of 100,000 kilometers per hour. Right? Compare that to an observer on the surface of the earth. Mount Everest is not moving at all. But for an observer on the surface of the sun, Mount Everest is moving with 100,000 kilometers per hour. But that's not the end, because the solar system itself is moving around the center of the galaxy. The galaxy itself is moving away from the center of the universe, and so on and so forth. So different observers in different places in different situations will report me different numbers when I ask them what is the velocity of Mount Everest. An observer on the surface of the earth will say 0. If the observer is on the surface of the sun, he will say 107,000. So I hope you are convinced by this point that motion is relative, velocity measurements are relative. All right, before we move any further, I want to introduce you to a couple of terms that we will be using going ahead from here. So in the examples we took previously about trees and horses and Mount Everest and so on and so forth, we had an object which was being observed by a bunch of people. There were a bunch of people who were observing something like Mount Everest or trees or horses, right? And after making an observation, they would report me a number, which is velocity or something like that. So these people who make the observation, they are called as observers, right? Your friend in the horse case, observers on the surface of the sun, moon, earth, those are all called as observers. Whereas what is being observed, the subject of the measurement, such as the trees or the horse or Mount Everest in the examples we took, these things are called as events. All right. In this example, the event is the horse running, whereas the observers are you and your friends making observations. And each observer is said to have a frame of reference associated with them. In simple terms, the frame of reference of an observer is their viewpoint. And let me quickly give you a couple of sentences as examples to get familiar with how we use these words in physics. So I can say that the horse is moving. If I label you and your friend as A and B, I can say the horse is moving 70 kilometers per hour to the left relative to observer A. Now observer A is you are an observer, whereas the horse highlighted in red is an event. The horse running is the event. And I say the horse is moving 70 kilometers per hour to the left relative to observer A. I can alternatively say, equivalently, I can say the horse is moving 70 kilometers per hour to the left in the reference frame of A, relative to observer A in the reference frame of observer A. These are equivalent usages. Right? I can say the horse is moving 70 kilometers per hour to the left relative to observer A, but the horse is at rest relative to observer B. Or the horse is in rest in the reference frame of B, but the horse is moving to the left in the reference frame of A. I hope you understand how we use these terms. So let's go ahead. So through the examples that we saw so far, we have understood that when it comes to motion and velocities, different observers are going to report different numbers in their frame of frames of reference. In the velocity of the same object, measurements done on the same event are going to have different values in different reference frames of different observers. But is there any connections between the numbers that these people report? Suppose you tell me one number and your friend tells me another number. Is there any relation or connection between these numbers for the velocity? And the answer is yes. We can have a relation between the measurements made by two different observers if we know the relative velocity between them. We have a neat formula for that. So if we have an event, if we have an object and two observers measure its velocity, the first observer tells me that the velocity is v and the second observer tells me that the velocity is v prime. I can connect them, I can relate them if I know the velocity of observer b in the frame of observer a. If that velocity happens to be u, then v prime is equal to v minus u. This is a very simple equation. Let's try to see an example to understand this. Right. So we are in the Masai Mara National Park, Tanzania. A cheetah is chasing a Thompson's gazelle. Right. A cheetah is chasing a Thompson's gazelle, and a wildlife photographer is shooting them. This wildlife photographer measures the velocities of the cheetah and the Thompson's gazelle. In the photographer's frame of reference, the cheetah has a speed 80 kilometers per hour relative to him, while Thompson's gazelle has a speed 90 kilometers per hour in the same direction relative to the photographer. So now the question is, what is the speed of the gazelle relative to the cheetah? Let me restate the question. In the photographer's frame of reference, the gazelle has a speed 90 kilometers per hour. What is the speed of the gazelle in the cheetah's frame of reference? I can find this if I also know what is the speed of the cheetah in the photographer's frame of reference. Alright, we can identify the photographer and the cheetah as two observers and the running gazelle as being the event. And we can just use the formula we just discussed about. Out of common sense, you might tell me that it's 90 minus 80, and that's exactly what our formula does here. So v bar is the velocity of the gazelle relative to the cheetah, while v is the velocity of the gazelle relative to the photographer, and this u here is the relative velocity between the cheetah and the photographer. And if I use my formula, obviously 90 minus 80 is 10 kilometers per hour. So the cheetah will say that the gazelle is running only at 10 kilometers per hour, but the cheetah is also running fast, right? Cheetahs usually can run faster than that actually. They can run as fast as 120 kilometers per hour, but maybe this cheetah is exhausted or something. So the idea here is that we can treat the photographer and the cheetah as two different frames of reference, and these three objects, the photographer, the cheetah, and the gazelle, are going to have different values of velocities in these two reference frames. You can calculate it, all right? So if I treat the photographer as a reference frame, in his own reference frame, his velocity is 0, which is obvious, right? The cheetah has a speed 80 and the gazelle, Thompson's gazelle, has a speed 90 to the right. Whereas if I take my cheetah as the observer, if I move to the reference frame of the cheetah, I see that the cheetah has a speed 0 in its own frame of reference. In fact, the reference frame of cheetah is defined by the reference frame in which the cheetah is not moving. In the cheetah's frame of reference, we just calculated that the Thompson's gazelle has a velocity 10 kilometers per hour to the right of my speed. Whereas the photographer in the cheetah's reference frame will be moving to the left with 80 kilometers per hour. Alright, in the photographer's frame, the cheetah is moving with an 80 to the right. In the cheetah's frame, the photographer is moving to the left with an 80. Right? So these are two frames of reference. The photographer's frame of reference here in blue and the cheetah's frame of reference here in orange. And we can go back and forth between any measurements made by the photographer and the cheetah using the formula which is discussed. Alright? So far, we have been talking about velocities. But we know that velocity is nothing but distance traveled by time taken. So if two observers measure two different values for the velocity of the same object, either they are measuring different values for the distance traveled by the object, or they are measuring different values for the time taken, right? So remembering that velocity is nothing but distance traveled by time taken, we can do a little bit mathematics, multiply the whole thing by time, and reach this conclusion. Notice here that x is the distance traveled as by an object as measured by one observer, while x prime is the distance traveled by the same object as measured by the second observer. However, time here is treated as an absolute quantity, right? And I will justify that later, and we will see how that idea is abandoned later on as well. So As soon as we write down an equation, the best thing to do is try to get to an example and see how the equation works. So let's do that first. So here in this example, we have our friend Newton. Right? Newton is being chased by a dog, but he doesn't know that he's being chased. He is busy thinking about why do apples fall, so on and so forth. He's unaware of anything. Newton stands 130 meters away from the stationary gate of a house. He doesn't know that the dog is chasing him. The dog starts from the gate and runs towards Newton 25 meters per every second. Now 25 meters per second is the velocity of the dog with respect to the stationary gate of a house. Right? After 3 seconds, how far does Newton stand from the dog? Now we can use the equation from the previous slide to answer this question. Here, the stationary gate, the gate of the house, is one reference frame, while the running dog is another reference frame. And Newton, thinking about apples here, is the object being observed. So in the reference frame of the stationary gate, Newton stands 130 meters away. I want to know how far Newton stands uh, from the dog in the dog's frame of reference after 3 seconds. If we use the formula we just discussed, here x prime is the distance of Newton from the dog after t seconds, and t is 3 seconds, which is given to us. 25 is its speed. Plug in all the values, and we'll figure out that after 3 seconds, Newton stands 55 meters away from the dog. He better run if he doesn't want to get bitten by the dog, right? So now let's make sense out of the equation we just discussed. So x and x prime are the distances of the object being observed from two different observers after time t, right? This equation relates distance measurements made by two different observers, length measurements. However, time t here, we can ask whose time? Time is measured by first observer, or time is measured by the second observer. In classical physics, nobody cared about it. Time was treated as an absolute quantity because you can have two identical clocks, give it to two people, and ask one person to start the stop clock and sit in a room, while another person to start the stop clock and go on a trip on a bus or something, and come back and you see that the clocks are measured the same time. Different people measuring time differently doesn't make sense, right? So time was treated as an absolute quantity, just like the number of apples in a basket. It doesn't make sense for one person to say there are 3 apples and another person to say there are 4 apples. Similarly, by common sense, it doesn't make any sense to say one person measures 3 seconds, another person has already spent 4 seconds. Time runs the same way for everyone. This was out of common sense. However, later we will see why people had to abandon this idea. So far we have been discussing in one dimension. We can extend this to 3 dimensions. If motion is happening in the x direction, only the distance traveled in the x direction will be reported differently by the observers. In the y and z directions, there won't be any change. The two observers will agree. And we have also agreed by the use of common sense that the time measured by them is also going to be the same. So this equation that we have been discussing so far is what is known as a Galilean transformation. A Galilean transformation helps us transform from the reference frame of one observer to the reference frame of another observer. All right. So, having learned this much, so having learned this much, we now know enough to ask ourselves, why did the special theory of relativity come about? So we have reached the first of the two important principles that led to the formation of the special theory of relativity. Known as the first one is known as the principle of relativity, which goes something like this. All motion is relative. We saw that. We saw that with the sun and the earth. We saw that with the moon. We saw that with Mount Everest. We saw that all motion is relative, which means the state of motion of an object, the velocity with which an object travels, uh, depends on whom you are asking, right? So if I want to conduct an experiment which involves measuring velocities of objects, suppose I am doing an experiment in which I have to drop balls, and I measure the velocity of the balls. That measurement is relative to the frame of reference of my laboratory. If I set up a laboratory on the surface of the Earth and set up another laboratory on the surface of the Moon, and if people conduct experiments, people do astronomical observations from both the laboratories, they are not going to agree about the state of motion of different objects, such as different celestial bodies, for example. But I can ask a question now: Which laboratory is the correct laboratory to do experiments? Whose numbers should I trust? And the answer is there is no special observer, right? So any uniformly moving observer is no more special compared to another observer for describing motion, which means a laboratory situated on Earth, for example, is not any special compared to a laboratory situated on the Moon for describing the motion of, say, Venus or the Sun or something like that. Physics better work no matter where you are. The important thing is the observer has to be uniformly moving, which means their velocity should not be changing. If their velocity is changing, we will enter a certain complications. So let's start with simple things, so right? We can solve the complications later. For now, if an observer is moving uniformly, they are no more special compared to another observer for describing the motion of objects. Now, this creates a requirement for laws of physics. A good law of physics must work in all uniformly moving reference frames. If a law of physics is a good law, it better work in multiple reference frames, right? I wrote down an equation. The equation works when I conduct an experiment in my laboratory, but it does not work if I conduct the same experiment on the moon or in an international space station. In such a case, the equation I wrote down is not a good one. Right? So a good law of physics must work in all uniformly moving reference frames. By the way, uniformly moving reference frames are also known as inertial frames. I'll be using that word from here on. So this principle here highlighted in red is called the principle of relativity, and it is a very fundamental principle, so to speak. And many laws of physics agree with the principle of relativity, starting with Newton's laws of motion. Newton's laws of motion work in all sorts of uniformly moving reference frames. You can conduct experiments on a laboratory on the Earth, a laboratory on the Moon, a laboratory in an international space station. Newton's laws of physics will work there, specifically Newton's second law. And here I have given a brief proof for what I just said. You can pause the video and go through it, but I'll be skipping it for now. And just like Newton's laws, most theories and most laws in physics agreed with the principle of relativity. They worked in different reference frames. But there was one young theory which was developed in the 19th century which did not agree with the principle of relativity, which was Maxwell's theory of light. You see, this Thomson's Gazelle, Mount Everest, and Sun and the Moon, all these things that we are talking about, we see them because of light. And philosophers and physicists had been arguing for centuries as to what is light made up of, what is the nature of light. And as a result of the accumulation of work done by many scientists such as Michael Faraday, Coulomb, and Ampere, and so many people, by the end of the 19th century, this guy over here, James Clerk Maxwell, was able to come up with a theory of electrodynamics which predicted that light is in fact electromagnetic radiation. It is a disturbance, it is a wave-like disturbance in the electromagnetic field. If you don't know what electromagnetic field means, it's okay for now. Later you can go to the internet and search it up. But what is important for us is to know that according to Maxwell's theory, light travels in space with a constant speed of 299792458 meters per second. Right? Light has a constant speed, and this speed does not depend on the observer at all. It does not depend whether you are looking at light standing on the surface of the earth or in outer space or on the moon, and so on and so forth. You will always see light moving at this velocity if Maxwell's theory were to be true. And Maxwell's theory was a result of century-long work. It was experimentally verified. So and this proposition that light travels in the same speed, which does not depend on the observer, contradicts the principle of relativity, contradicts common sense. Because suppose I throw a ball, I say the ball is traveling very fast with a certain speed. A person traveling in a car, for example, when he sees the ball, he will say the ball is traveling very slowly because he is moving in a car. So by the same token, I will expect that if I send a pulse of light, I see that light is moving at this speed here, 299792458 meters per second. I expect that if a person is traveling very fast, he will see that light is moving slower. We had that formula, right? V bar is V minus U. So if a person is moving very fast, I expect that they see light traveling slower. But Maxwell's theory predicts that this shouldn't happen. Different observers do not report different values for the velocity of light, unlike the velocity of trees and horses and balls. which means the speed of light is not relative but an absolute quantity, just like the number of apples in a basket. Everybody had to see three. Everybody had to see three apples. Just like that, everybody has to see the number 3 into 10 to the power 8 when they measure the velocity of light, regardless of how they are moving. So the velocity of light, the speed of light, is something different from the speed of balls and cars and trees and Mount Everests and things like that, because uh, when you measure it, you are not making a relative measurement. This clearly violates the principle of relativity. This clearly violates our common sense. For instance, if a beam of light was traveling like this with 3 into 10 to the power 8 meters per second, if you stood here, you made a measurement, you would say the speed of light is 3 into 10 to the power 8 meters per second. If you had a friend who was traveling in a rocket or a space shuttle with a very high speed, in your frame of reference, he's traveling in the same direction as the light beam with the speed of 2 into 10 to the power 8 meters per second. Now, if we apply the Galilean transformation laws, which we just looked into a couple of minutes ago, it is necessary that, first of all, in his own frame of reference, his speed is zero, v minus v is zero. But what about the speed of light? What will your friend see the speed of light to be? If we use the same laws of Galilean transformations that we talked about, the speed of light in your friend's frame of reference should be obtained by subtracting the relative velocity between you and your friend from the speed of light as you measure it, which means c minus v. Your friend, while you see that light is traveling at 3 into 10 to the power 8 meters per second, your friend will see that light is traveling at a speed 1 into 10 to the power 8 meters per second. C bar is not equal to c. Your friend will report a different value of velocity compared to you, which will make the speed of light a relative quantity, which clearly violates Maxwell's prediction that the speed of light is an absolute quantity. It is not relative, right? So the principle of relativity, Galilean transformations, they are violating Maxwell's theory. Maxwell's theory is violating the principle of relativity. These two theories are not in agreement with each other. Okay, these two principles, the first is the principle of relativity, which says that the laws of physics must be obeyed in all inertial reference frames. And the second principle, which is called the principle of light constancy, which says that the light has a constant absolute speed of 299792458 meters per second in free space. We have seen that these two principles are in a contradiction with each other, because the principle of light constancy is not obeyed in all reference frames if we go with the Galilean transformation laws, and thus it contradicts the principle of relativity. This problem was known to physicists by the time it was 1890s, and people were running through their heads to get a solution, because there was a problem and you had to find a solution. Two well-established theories in physics were violating each other. The Galilean transformations and the principle of relativity, developed in the 1600s, well established for almost 2 to 3 centuries. On the other hand, there is the theory developed in the 19th century, a quite young theory of Maxwell. And people had to, since the two theories violated each other, one of them had to be updated, right? Most people were more faithful in the principle of relativity and doubtful of Maxwell's theory, because Maxwell's theory was quite young, whereas the principle of relativity was old. It was almost 250 years old by the time, well established. Most people thought that maybe there is something wrong with Maxwell's theory, and they tried to come up with different solutions, but it did not work out. And then enter the first decade of the 20th century, came arguably the best physicist of the 20th century, and arguably the best physicist, one of the best physicists we have seen so far, Albert Einstein. All right. Uh, Before I go any further, let me just give you a brief introduction of Einstein. So Albert Hermann Einstein, he was born on 14th March 1879 in Ulm, Germany, which means he'll be celebrating his 145th birthday today. Of course, if I upload on time as planned, nothing goes wrong. Einstein graduated in 1900 with physics, but he did not get a job related to physics. He had to work as a patent clerk in the patent office, but he did not abandon his interest in physics. Despite having a job that does not require him to study physics, he continued poking his head into contemporary problems in physics, many problems. One of them was this problem that we have discussed so far, the contradiction between the principle of relativity and electrodynamics. the principle of light constancy. So Einstein spent many years worrying about uh, how to solve this problem. Unlike most people of his time, most scientists of his time, who were doubtful in Maxwell's theory, Einstein had faith in Maxwell's theory. He believed that Maxwell's theory was correct. What must be changed? Maybe it's the loss of Galilean transformation. Maybe that's what requires an update. So Einstein looked into that direction. He he spent many days thinking about this, sleepless nights and effort. And he had to work in a patent office to start with. In the meantime, he spent his time worrying about these things. And on one fine afternoon, during a lunch break, Einstein had the eureka moment of his life. He realized something very profound. As soon as he got back home from office that evening, he took his pen and paper and started working out. What he realized was that in the Galilean transformation laws, we were taking for granted that the measurement of time was absolute. We were taking it for granted that two observers will measure the same amount of time. Einstein thought that's where the problem was. He said, we need to change this. We need to do something about this. In his own words, he said, time is suspect. Time is relative. Time is not absolute. And he took his pen and paper out. He worked out some mathematics. He took some examples, and ultimately he proved it that Maxwell's principle of light constancy and the principle of relativity can be made to agree with each other. That we can have the speed of light be absolute. We can have the speed of light be the same in all reference frames if we abandon the idea that time is absolute. The velocity of light can be made absolute if we abandon the idea that time is absolute. If time were different for different observers, then light could be shown to have a constant speed, an absolute speed in all reference frames. And this was a profound breakthrough. What exactly did he do? How did he prove it? We will see next time. Right. So I really wish that I could tell you all of it in a single go, but have some time constraints. So I'll try to get back to you people as soon as possible. Okay? Until then, try to think about it yourselves. Try to think about what you could do with this piece of information. Try to see if you can solve the problem. All right. So before I go ahead, I just want to wish a very happy birthday to Albert Einstein. I don't know if this will be an exact birthday wish or a delayed birthday wish, but in either cases, happy birthday to Einstein and thank you for giving us this elegant theory. And I will see you guys next time. Until then, keep thinking about science, share it with your friends who might be interested, and I'll see you guys next time. Stay tuned until then. Stay always awesome.